in continuations 3, but I'm not going to do that right now because it'll make more sense when we get into the next homework. So I'll boldly move on into continuations in Scala. And we know everything about CPS that we need to do to model through that. So so Scala has adopted continuations, and not as a tool for everyday programmers. So it's not expected that Joe programmer is going to write any code at all with continuations, but as a tool for people who build other tools. Scala has these two aspects, that it aims to be a language that's easy to use by the masses, the people who will run out and buy a copy of Scala for the impatient, and then there's a much smaller number of people who program libraries that other people will use. And so the expectation is that there will be some library builders out there that will find continuations useful for what they want to achieve. So when you look at the Scala features and you say, this makes my head hurt, no one is ever going to program like that, that is absolutely right. So it's only a small number of people who will need this. And what could they do with continuations? Well, someone could write a continuation-based web server, for example. Now, Scala cannot have real continuations. Why not?
Because it doesn't have a concept for it.
Well, they could add one in.
Maybe it doesn't store things the way we need.
Yeah, that's kind of the right intuition. So Scala runs on the Java virtual machine. So Scala can only do what the underlying Java virtual machine can do. And to implement continuations, you need to have a way of hanging on to a particular state in the program, runtime stack and all, for an indefinite amount of time. And there is absolutely no way of doing that in the virtual machine. There's no command to take a snapshot of the stack. And it's a destructive, it's a mutating stack that, as function calls happen, they override what was there previously. And if you wanted to go back to a previous point in time and keep that entire history, there's just nothing in the virtual machine that lets you do that. And the virtual machine will never add it on. It's just so outside what the scope of the JVM is. So they have to fake it. So they have continuations, kind of. And the way they do it is they use CPS rerun. So they will take code that looks like continuations, and then they rewrite it in the continuation passing style. That means they will find out what is the computation that's being expressed and how can one extract that. So, and we'll need to know a little bit of that as we go through what Scala does, because as you'll see, there's some limitations that come from that. The other thing that Scala does, unlike the scheme, is Scala is a strongly typed language. All expressions have some value, and that's particularly bothersome with continuation-based expressions. They have a value, they have a type, and the types you need to worry about how they flow as the program gets composed. So the strong typing is not the happiest thing to have with continuations, and so we'll see the types being attached to things in a way that's maybe a little complicated. So Scala uses a slightly different mechanism to express continuations. They don't have call CC. They have a pair of operators called reset and shift. So all continuations in Scala are delimited. There's no such thing as popping out at the REPL. You set a continuation boundary. So reset sets the boundary that the continuation will only capture things that are enclosed in the reset. It's somewhere inside the reset, and it may be inside the same method, or it may be inside a method that is called by the code in here. Somewhere in the reset, you have a call shift. Shift is the thing that takes the continuation, and just as with call CC, it's being passed as a parameter. So here's the continuation k, and now you can do something with it. So it gets passed as a parameter, and then we do something. So when we execute the code, we come through here in the reset. We come through in the reset. We get into the shift. At this point, we have K at our disposal, and we execute the inside. And then it jumps over this after part, and execution pops out again here. So at this point, we can, for example, stash away K for later use. So that's what most typically is done here. I don't know. I think they're operate. I think they're functions.
So you can give any name?
Well, they could have given them any names. They could have called them Fred and Wilma, but they decided to call them reset and shift because that's what's used in another library. Yeah, so I particularly have no idea why they're called reset and shift. I've never really understood that. There must be some way of thinking about them that makes you think of resetting and shifting. I've just taken them as kind of arbitrary names. So yeah, Fred and Wilma. So the Fred thing delimits the outer block, and when you get into shift, then you're being handed the continuation. You can stash it away. You can do whatever other things you might need to do at this point, and then at this point here it exits. So when you call the continuation, so we exit here. When doing the reset. Come in here, come into the before, come into the shift, and then you get up. When you call the continuation, then it looks different. Then you jump into here. You execute the inside, and you return. Sorry. When you call, you replace this whole thing here with the argument, and then you execute out. So we'll see an example in a minute. Now, I know it all sounds weird, but they had to cram all of the various bits and pieces into some syntax, and that's the syntax they chose. So the shift can actually be inside some expression, so that it often happens, because when you call K with some argument, then what happens is that this thing here is replaced with the argument, and then the surrounding expression is executed with that argument. So now it can also happen that K, when it gets executed, then it again runs into the shift. And this would happen if you're inside a loop. So let's say that this expression here is some looping expression, say it's a map. And then you get into the shift, and then you get back into it, and at that point you again pop out at the end of the shift. So every time that you get into the shift, then you jump back out. So the shift kind of is an automatic return, which is kind of convenient to have. When we did this with call CC, when we wanted to get in and out, we always had to set up two continuations, and here you kind of get to one of them for quick. And also notice that when you call K, that if you don't pop out because of a shift, but if you simply kind of trundle into the after and then you hit the reset, that's where it ends. So you always end at a point inside the program. You never go back all the way to the REPL or out of the program. So those are the basic features. Let's put them to work to get some feel for it. So let's look at this gruesome example here. So we have a reset. We don't do anything before. We have a shift. The shift gets the continuation parameter. Here it's typed as going from integer to integer. And now we're calling k of 3, and then we add 2 to the whole thing. So let's see what the heck this is doing. First of all, let's find out what the continuation is that's being passed. That's the same thing as in scheme. You take the we used to take the call CC, now we take the shift. We say that's the whole. That's the thing that is being surrounded by stuff. And so k is the whole plus 2. So therefore k of 3 is 3 plus 2 plus 2.
Is it lambda whole in the body?
Sure. So it is lambda. Yeah. But in the world of Scala, we say underscore plus 2, so here it's the same whole plus 2. So so when I execute this thing, I get into the reset, I get into the shift, I compute k of 3, and the answer of that is 7. And then I reach the end of the shift, and because I'm at the end of the shift, I get kicked out of the whole thing, and my value is 7. So this plus 2 here, I'm not executing.
Because it's called from inside.
Well,
There's no
even if I did, even if I never called k here, I still wouldn't get in there. It's just because when you get into a shift, you always get out of the shift at the end. That's the rule. So this is, of course, a silly example. That was just to kind of show what the pieces look like. What you normally do is when you execute the reset, then you capture the shift. So I have that over here, where I set some variable that captures the continuation. I have to type it correctly. I have to say it goes from in to in. At the beginning, I don't yet have any value for it, so I set it to null. I get into the shift. Now I have k, and here I stash it away. And so over here, I'm not doing any other action inside the shift. That's probably normal. And when it executes this, then no particular value is returned because this thing has time unit. So now that I think about it, I would be able to say this a little bit more concisely. I should be able to say so I'm just going to say k1 equals this whole thing, because in this case it returns the k. That way I don't have to set it to null first. Yeah.
Can you explain the point again which you are saying that after executing the shift it comes out?
The last value of the last thing inside the shift is the result.
And what about the plus 2?
It is not part of the execution when you go into the reset.
So then how is it in the previous example, how is it even getting 3 plus 2?
There's two different things going on. There's the question of what happens when you execute the reset, where it meanders this way through, and as soon as it gets to the shift, it bails. And then there's the question, what is k? Unrelated question, what is k? K is what you get when you take the entire shift and replace it by a whole. And then everything else around it, that's the function that goes from that where the whole is the parameter and everything around it is the body. That's what k is.
And then
So this plus 2 here is important to specify what k is.
So when we are executing reset, when it goes inside the shift function,
Yeah.
there when it sees k of 3, that's where it recognizes that that whole thing has to be replaced.
Well, it's being passed. No, it's being passed k, whether or not you use it or not. It's being passed k.
Correct.
So that means that the compiler needs to figure out what k is. The compiler has figured out what k is. It's the function blah plus 2.
Right.
Yes.
3 plus 2 and then that will be
So it manufactures out of this context.
And it
see, the complexity in the syntax is that one syntax tries to do two things. That on the one hand, you have the control flow as you go through, and on the other hand, it tries to describe what the continuation is. And it's always like that. When you have a call CC, you get cast a function. What is that function? It is what happens when you punch out the call CC and you say, get me back to that point. And so it's kind of the same thing. It's the continuation here really is get me to the point where this thing is being used, and then keep on computing. So the only point that I was making here is because I don't actually have to stash it away here. I could compute it like that, but I think that's an anomaly. I don't think that's generally. All right, so over here I've done it in the more traditional way. I've stashed away my continuation, and now I can call it as often as I like. So K1 is now the function that adds 2. Now we know that in practice we don't care about these trivial continuations. We're going to have a continuation. Like the iterator is always a good model, where you jump back and you deliver some result. But you do need to kind of save it anyway. So the mechanics here are like that. And then so far not dramatically different. Notice the types. This K here is typed to consume an integer and to return an integer. And so in this case, of course, that is true because we're adding 2 to something. That is the outermost thing in the reset. So we're delivering an integer, and in order to be able to add 2, we need to kind of give it an integer.
So after a requirement, we can have different types.
You can have any types you want. You can have a continuation.
Depends on the computation.
Exactly. But it's sometimes a little confusing to see what those types are, as we'll see when we put this to practice. In this case, it's trivial, but in reality, it can be a bit of a challenge. So that's why I'm having the type cheat sheet, because I have this problem. So we have the reset, we have the before, we have the shift. The shift we have to specify, because the system will not be able to guess generally. We have to specify what we want. We have an input type A and output type B. So what is A? A is the type of what the shift is going to be replaced with. Remember, we punch out the shift and we stick in some value. And that value is going to have type A. So A has to make sense in whatever this thing is being used for. So if it's used for, like, by adding 2, what we had the +2, then A would have to be an integer or a number. Sometimes it happens that we're not really combining the shift, it's just our entry point and we do more work afterwards, in which case A would just be unit. That means we don't care what that value is. It just says, jump here and then go on with the next step without actually using this value. In that case, it would be unit. And so B is the result type, and that is the type that the function returns. So again, remember, the function we dump into here where the shift would be, and then we just work through in the normal way. So it is whatever that value is, so that's the value of after. And now reset also has a value because it's an expression, and reset is what comes out from in here. So generally this should be easy enough, but now there's going to be a situation where when you call some method f, which has a reset, which calls g, and then g has the shift. And it turns out that sometimes we want to set things up in this way. Now, in this situation, because of the nature of the CPS rewrite, we have to annotate G as saying that that G is kind of a special method. It's a method that is being completely rewritten by the CPS transform, and the compiler needs to know that that this is the case, and you have to annotate it by saying at CPS, and now sorry, CPS param BC. And in almost all cases, it turns out B and C are the same. In that case, you can just annotate it with CPS. We'll see an example in the next slide. So here's what happens whenever I do this. I write up my program. I can't be bothered to think about what the CPS annotations are. And I get a completely incomprehensible error message from Scala that says something about CPS, and at that point I get out this cheat sheet and I start marking up and say what these types actually should be. And I find it confusing every time. I don't know why. It doesn't look confusing on the slide. So, as an application. So, we're going to do the usual tree walk example and rewrite it with Scala continuations. So, normally, you know what we do in the tree walk. We've done this in several examples. You visit a node, and you visit each of its children. I don't remember if this is a binary tree or not. You visit the children, and each time you apply some function. And that gives you a functional style, but it means that the function gets applied to all of the nodes. So I want to now use continuation so that I can turn it into an iterator where I first visit one and then I visit the next, and then I could stop my iteration. So let's look at the code. And I've done this here to make I needed to have some source of trees, and I didn't want to write a tree class and all of that because it's all confusing, so I just used directory trees. Plain old Java directory trees. And that's something we're going to be doing for several other examples, so let me take a couple of minutes to introduce the way this works. So in Java, you have objects of type file, and a file is either a file or a directory. That's the way it is. You can tell whether it's a directory. There is an isDirectory method. That is true when it's actually a directory. And when it is a directory, then you can use the list files method that gives you an array of files. And which may again be subdirectories, or they may be simple files. So here in my process files method here, I check whether something is a directory, and if so, I call process directory, and otherwise I process the individual file, and in the individual file I'll do whatever. So I'm being given a function. Where's my function? Oh, I guess I'll just hard code it in the process file. I could do it in a more functional way where I get that function as a parameter, like we had in Scheme, but here I chose not to do it. So process file is where I do an individual one. And over here, I'll do something a little weird where I call this function itself recursively. And I'll come back to the reason why I'm doing that in just a minute. So right now, you see I'm taking off the head. I'm checking if it's a directory. If so, then I call this process directory function. Otherwise, I call this process file function. And then I go to the tail so that I can keep on doing this. You might say, why isn't he just doing map and not telling me the So process directory simply calls process files with this thing. And I could have built this in here. I just wanted to simplify it as much as possible. So I could have had that. Yes, sir. I could, but I didn't. So that's the basic processing. Now let's look at what I do for each individual file. I print the file. That's the only action that I'm taking here. In reality, I should make it so that I can do arbitrary stuff instead of just printing. And then I want to return to the world. And the way I can return to the world is I can put in a shift. Because when I run against this shift, then I will jump to wherever the reset was, which we'll find in a minute. It's here somewhere. So at this point here, it jumps to the reset. And that was the whole point of putting, that was one of the 2 points of putting that thing in there. The other thing is, later on when I'm done with an iteration, and I want to go back in, then as it happens I want to go back to the same spot. So the jumping here I got totally for free. I didn't have to take any continuation. Unlike what you've seen in Scheme, where you had to take a continuation to jump in and a continuation to jump out. So the jumping out I get for free, the jumping in, no, I have to stash away this continuation. And so this weird reset shift syntax is done because this is such a common situation that you often want to say, later on I want to get back into this point, and of course, because I want to get back in later, that means right now I want to get out. So that's why all I'm doing here is I'm stashing away my continuation. So let's find the reset. And it's right here. So what it's going to do is, it jumps to this point. So we just keep calling the continuation, and each time it's going to jump to this point, exit, and print the next one. Yeah?
So when it comes back to reset, it comes out of reset or to that line process?
Oh, it comes back to here.
So, comes
So I shouldn't say it jumps back. What it does is it.
rest of the computation.
Yes, but so that's so it gets to. How do I explain this? So yeah, it comes to here. So all right, yeah, that's so it does. It ends. So I'm not saying this very well. It ends the computation. So it does immediately returns. This is a function, right? So the continuation is a function, and so it returns out of this function with the value that's the last statement in the shift. So I guess saying it returns to the end of the reset is kind of a poor way of doing it. It simply returns out of that function. Continuation is a function. We're building a function, and when it runs against the shift, then the function terminates and returns the thing inside the shift as a value.
Mm-hmm.
So it's not really a good thing to say that it kind of jumps to the end of the reset. That jumps to the end of the function.
Function. In this case, it's outside the reset.
Yes, because it's a function. It returns this thing as a value.
So here, when you are calling build and again, when it comes to this
Yes.
line, you go back there.
Yes?
Um,
So, in fact, where do I go? I go
That
as if this
is
thing here was not here, and so I go here.
correct.
Yes?
In this case, there's nothing there.
Well,
but,
that's not quite so. I mean, it's the middle of a loop. So I am, this thing is crunched out. I get here, and I am inside process file, and my computation keeps on going. So what happens? Process file returns to its caller. Its caller was here. And then it recursively, calls process files again. So I return to the computation. How long do I keep going? I keep going until I hit the shift again, which will happen again. At that point, I'm back out. My K1 returns again, and I'm returning whatever was inside the last line in the shift as my answer. Eventually, I'll be completely done and I will not hit the shift again. At that point, I will come out with out of process files, and I'll come out of reset. And at that point, I guess I would be running into the loop.
So, hold on.
Yeah.
So as what calls, you see every time the shift is called, a new continuation is set.
Yes, but it's the same one.
It's the same one,
Yeah.
but the point in the loop is different.
Yes, the history is different.
And what is the significance of I1 to 10 here?
Oh, I just wanted to print the first 10.
First 10 files.
Yes. So I wanted to show the benefit of having an iterator versus complete traversal. In the complete traversal, I would print all files. I would have to go through the entire file system. But if I just want to see the first 10, then having the iterator is nice. So now to the types. So let's look at the return type here. What's the value? What's the type of this type? Unit. Because in Scala, an assignment has no value. So this thing has unit, and that means that the return from the continuation should be unit. What do we feed in? We're also feeding in nothing, and so that means that we're not putting any value inside this thing, and that explains this unit. And finally, at the reset here, there's no value that we're interested in either, so we have a unit here as well. So now when we look at the type cheat sheet, we find that A, B, and C are all unit. That's a common situation. And so that's now we need to annotate this thing here as CPS of unit. Let's see, where do we have to annotate first? I need to annotate this thing here as CPS of unit because it contains a shift. If I did not do that, then the compiler would say, well, it contains a shift and it's not being annotated. Now, process file is called inside process files. And that means I need to annotate this thing as CPS unit as well. It too needs to be rewritten to CPS stuff. And process directory calls process files. And it also needs to be annotated as CPS unit. Now that explains why over here I am not able to use map. So over here I would have liked to use map or for each instead of doing this loop here. So I would prefer to say, let's say for each, right? So I would like to say for each files dot for each, and then I'd like to give like a function that says let's do this in the usual way, or maybe I would have liked to use a for yield for loop, which gets translated into a for each. And I can't do it because for each is not CPS. And so the analog for that, if we go back to the slides from last time, if you remember this slide here, I said all of the stuff here, this transformation here, is going to work beautifully, provided the square function here is not a normal function. It's not the lambda x. So here when you see square, you think, oh, this should be lambda x dot star xx, or what do we have, lambda x star xx. But instead, it has to be one of these continuation eating functions. And so when you have it like that, then it works. And so that's that's an unfortunate limitation in when you do the CPS rewrite strategy, that you are limited to only calling functions that themselves have been marked as CPS rewrite. So I could implement for each. I could implement my own version of for each, then a tag with @CPS whatever, and then it'll be transformed in this way as well. But I did not do that. Yeah.
So here, the reset function we're calling it in the main. So why is that not tagged as CPS?
Oh, the reset. I see. That's a very good question. The reset delimits the rewriting process. It sets the boundaries for between the normal world and the world of CPS. So the reset. Once you have a reset, then everything that's outside does not get rewritten. Yes, and if I didn't have a reset here, I don't think it would work. I don't think I could have a main that is at CPS. It would not be the regular kind of main. The JVM would never call it. So you do have to have some reset outside. So and we'll see. In the lab we'll look at the code that gets generated, and frankly the code is messy and unpleasant. So one doesn't typically look at it a lot, but you can kind of glimpse at where this rewriting happens. So let's do the lab. So in this lab, we can't just use the REPL, unfortunately. We have to compile and we have to run. So you need to use Scala C and Scala. And so you need to put this thing into some file. Now I call it sleep example. You need to compile with this flag here, this continuations enable, because I believe it's not yet the default. Double check that though, they might have fixed that in 2.9. These slides are still from 2.8. And then I'm giving you some program, and what I want you to do, of course, is try to figure this stuff out first before, and then run the program. So before actually running the program, do me the favor of reading through it first. Try to reason in your mind what should be happening here. Now, I hope that everyone has a basic idea of how threads work, because we're using threads here. So let me just see if that's the case. So, so what's the sleep method do? It does some shift stuff that we're ignoring here for now. It makes a runnable that sleeps and calls k, whatever it is, and then it makes a new threads, and then it starts it. So what you need to know is that what now happens at this point here, so someone called sleep, and so now we're inside sleep, and now we're calling start on this thread. So at this point we now have two actions in parallel. Sleep returns and prints something, and at the same time we're now inside this run method. So now we're calling thread.sleep, and we're calling k. Thread.sleep just waits for some number of milliseconds. So it's going to wait for 2,000 milliseconds because 2,000 was passed with a delay. Delay is 2,080. And so these two things happen in parallel. Concurrent, yes. Yes, thank you. Yeah, there's no such thing as in parallel. Or there may be. You have two cores, so. There is kind of an implicit, so what I overheard saying there's no stashing, and I want to say that that's not quite so, because this runnable here captures k. It's a closure, so it captures this k from its enclosing environment, and so it does stash it away. Well, k is a value. Functions are values.
It's a function called k.
Oh yeah, but what is k?
It's a continuation function.
It's this thing,
Right.
and it's been captured in the scope. So it was implicitly actually assigned to some given field. because when it makes this object, it makes an anonymous object of some subclass of runnable. That object is going to have a field called K, and that's a copy of this thing. So it was stashed away even though it doesn't look like it.